So next section, or the next part of this section, is what you're going to see up here, still dealing with alternate infinite series and their convergence, but you're going to see the idea that these are going to be alternating. The alternating, pretty much if you look through every single problem right now, if you flip through the paper, you're going to see this little guy here, which we've dealt with in the past, that just shows that our function alternates, that this is going to bounce back and forth between positive, negative, positive, negative, positive, negative. All right, so that's what this gets into, and how can we determine if an alternating series is going to be converging? If you went back and looked through all of your previous notes, you'll see they do not alternate. These will now start. Well, the geometric, I guess, would, but yesterday, most of them, if it's not geometric, you wouldn't see those alternating at all. So for an alternating series, we're going to start with this idea. Does the following series converge? So if we look at this very first one, and then how do we know this? Hopefully we can look at this and right away say this is a no, because that's your harmonic series. Spent a lot of time on that yesterday, or whenever you watch the previous video. And everybody knows then the harmonic series diverges. If you go to the second one here, you're going to see the harmonic series again, but you're going to see the alternating harmonic. So let's write out, you're going to see it alternates, so this is called the alternating harmonic. So let's write this out. If n is a 1, you're going to get a negative 1 squared, so it's going to be positive, and then I would get 1 over 1. So the first term is still a 1. If n is a 2, you're going to get a negative 1 cubed, so that means we're going to get a negative 1. And then in your denominator, a 1/2. And then what should just happen just produces the alternating harmonic series. So our sign is going to alternate, and we continue to get the same series that we dealt with quite a bit in the previous set of notes. So up here is the harmonic, down here is what we call the alternating harmonic. This question is asking you to determine if the following series converges by finding the partial sums. So that's what I have over here. So if I ask you for what's the first sum here, that just means we add up the first term and that's it. So that's why our first sum would be 1. If I ask you what your second sum is, that just means you're going to add up the first two terms. So the positive 1 and the negative 1/2 together make a half. If I ask you for your third sum, you can verify this on your calculator if you'd like, but if we took 1/2, I guess that's pretty simple, 1/2 plus 0.333, you're going to get 0.833. So as we're doing this, I probably should have told you this as well. Draw in a little XY plane. So here's our x-axis, here's our y. And let's go back to graphing this like we did the very first day with all of these. Our first term, we got a sum of 1. So we would have been here. The second sum, remember, so the second sum, if this is 1/2 way through, we'll say, that's where our second term is going to be. Our third sum is 0.83, so that's going to be right around here. If we do our fourth sum, so now we're going to add or subtract that 1/4, add up all 4 of the first terms, that takes us to 0.583. So if this was 0.5, the fourth term should be a little bit higher than that. If we go to the fifth term, so we now add an additional 1/5, we now jump up to 0.783. So this was 0.833. So 0.783 would be just below that. And what we should start to see, let's do 1 or 2 more. The sixth sum would give you 0.616. So that's going to be just a little bit higher than this 0.583. And what we should start to see as we do this is that we don't necessarily know what it is right now. We could find it maybe, but we don't necessarily know right now what it is. But it definitely appears as if we are converging upon some value in here. All right. So even though we're bouncing one above, one below, above and below, above and below, each time the one above it and the one below it is converging upon some value in here. So this one, we would actually say converges. So alternating series is still a no-go. But if we deal with the alternating harmonic series, the alternating harmonic series converges. All right. So how would we know this without having to, do this process all the time and graph up all the partial sums? You have this little theorem here. So the alternating series theorem basically says that this will converge if the following 3 conditions are met. So the first one is all of your a sub n's better be positive. So this is our a sub n, and the reason that is important is because this should be the alternating part. So as long as this is always a positive number, this is what's going to bounce back and forth between positive, negative, this guy here. And it will then, if this is always positive, guarantee that our overall terms will continue to go positive, negative, positive, negative, positive, negative, so on and so forth. So this has to remain positive the whole time so that this would take us from positives to negatives, guaranteeing that we actually are dealing with an alternating series. Okay, so that's the first thing. The second thing, just so we understand that, a little harder to sort of understand what this is, but whatever, let's say n is a 1, then this would have been a sub 1. This would have been a sub 1 plus 1, so 2. So this would mean that, let's go to the term up, we can't quite get there, but basically what it means is this term would have to be greater than or equal to this next term. If n is a 2, then this would be 2 plus 1. So now that means the second term would have to be greater than the third term. What that really means is our sequence of terms needs to be decreasing. All right, so we've got to be decreasing as we go towards infinity. And then this somewhat goes hand in hand for the most part, that as this is decreasing, the only way this would work is if the limit of a sub n as n goes to this should be limit as n goes to infinity for our general term has to be 0. All right, so the big thing you're just looking for is, does this general term stay positive? And then does it have a limit of 0 that we decrease all the times towards that limit? And if it does, then this is going to work. So if we went back up here, if we went to these n values, all the integer values from 1 to infinity, would this guy always be positive? And it would. It would be the harmonic series, 1 over 1, 1 over 2, 1 over 3, 1 over 4. So when we throw this alternating term in front of it, that would guarantee that we change signs the entire time. And then if we kind of ignored this, does this series decrease? So 1, 1/2, 1/3, 1/4, that's getting smaller. And then not only is it getting smaller, the big thing is as n goes to infinity, its limit would be a 0. All right, so that's what we're looking for with the alternating series theorem. So again, I'm actually going to probably jump you to number 2 to explain this. So once we see that this is here, that it should alternate, that's what this term is saying. The only way that this will alternate is if this term is always going to spit out positive numbers. So if we throw in a 1, you get root 1 plus 1, 1 plus 1, that's positive. If we put in 2, so on and so forth, every n value from this 1 to infinity here is going to give us a positive number. So the thing that we then are concerned about, does this decrease towards a 0? That's the question that needs to be answered. And if it does, then it's going to converge. Goes back to our rates of change. As n goes to infinity, really the nth term test, did that a lot the other day. As n goes to infinity, this has a power of 1/2. This has a power of 1. So our faster growing function is in your denominator. We now know for certainty, we don't need the question mark here anymore, that this does go to 0, which is basically what we needed to determine. So this converges, and then all we would have to write is the alternating series theorem. You don't then have to list the 3 components of the alternating series theorem. 3, let's rewrite this first, -1 to the n plus a 1. This should be the natural log of 2 over the natural log of n. Let's start this at 2 now that I look at this, so it works out nicely. This is alternating, as long as if I throw in a 2 for my n and then 3 for my n, even though this does very, very, very slowly go to infinity, we have a constant in the numerator. So our faster growing function in this case is in your denominator. It's always going to spit out positive numbers. There's no way the natural log after 2 is going to give you a negative number. The limit of this as we go to infinity is 0. If we did the nth term test, n goes to infinity. So it satisfies what we need to satisfy. It's positive numbers all the time, and it always decreases towards a limit of 0. So this one converges. And again, alternating series theorem. All right, 4. This should tell us that we're going to alternate. Now all of these should be decreasing. Don't worry the fact that this one is a0. That would just mean the first term is a0. We wouldn't necessarily need to write it. And then the next term would have been like the natural log of 2 over a2. So that not a big deal that the numerator in this one is 0. Here it was just because the natural log of 1 would have given us an undefined value for our limits. It doesn't necessarily matter here. But we're alternating, or should be alternating. This will always give us non-negative numbers. Our faster growing function is in our denominator. The linear function n is going to grow faster than that logarithm function natural log of n. So the limit of this is 0. So this guy also converges. Oops. And then again, alternating series theorem. Getting lazy. Okay, 5. Again, this is alternating. Every n value I would plug in, 1 through infinity, these would spit out positive numbers. The only thing that has to happen is as n goes to infinity, if we do our nth term test, this has to have a value of 0. Hopefully we are to the point now where you're telling me, no, Mr. Pena, that does not go to 0, because we know that, let me get rid of this also. And I don't know why it does that every time I erase. Sorry. We know that the 2 to the n grows faster than n to the 4th power. So as n goes to infinity, as we do our nth term test, this limit is infinity. So this one would diverge. You really would, use the nth term test if we wanted. The nth term test. The limit of the a sub n term as n goes to infinity was infinity, and then not the 0 that it needs to be. 6, I'm going to rewrite this one so it's a little easier to see. This is a negative 1 to the n plus a 1, and then 0.1 is 1/10 to the nth power. And we want to determine if this converges or not. You now have a couple of options here, and this is going to present itself. And hopefully we're getting to the point, if we know these pretty well, let's not leave that, that you can use either or. Since we're doing the alternating series idea, let me rewrite this one more time. 1 to the nth power is still going to be a 1, and then I have a 10 to the nth power in our denominator. So if we do the alternating series idea, this is always going to give us positive numbers, the general term here. This then is going to alternate us from positive negative to positive negative. And then if we ask ourselves, does this decrease towards 0 as n goes to infinity? The answer to that is the definite yes. Your denominator is growing very quickly. Your numerator is a constant. So we could definitely say this converges. And then I'm going to start abbreviating this, alternating series theorem. Or we could have done this one yesterday without having to worry about the alternating series theorem, because, let me create some space here. I'm sure the page will jump up on me and annoy me. Okay, perfect. We'll rewrite it again. Negative 1 to the n plus a 1, and this is really just 1 over 10 to the n. We could say this is a geometric series. Hopefully we are recognizing geometric series now pretty quickly. So geometric series, I probably should have said it converges first. Squeeze that guy in there. Geometric series with an absolute value of r equal to 1/10, which is less than a 1. Either one of those would be valid. Same with number 7. You have two options here now. We're dealing with the alternating series theorem, so hopefully we can look at that one and right away say, yeah, this is going to converge, because when I start plugging in 1 through infinity, this expression here would always spit out positive numbers. We would also say as n goes to infinity with the nth term test that this would decrease towards 0. And since we're alternating, everything should be good. So alternating series theorem. Or this is a p-series with, you know what, let's not do that one. Okay, let's just leave that. It is a p-series. If this wasn't here, it's good. It gets into a little something that we haven't done that we don't have to do anymore. So let's just leave this as converging since it's alternating. Keep it simple. If that was by itself, then yeah, we would say that it's a p-series. 8. This should alternate us as long as this is always positive, which it would be. What we need to make sure of then is, would this guy, this general term in here, decrease towards 0? So if I ask you now, what is our limit here as n goes to infinity? We would hopefully recognize these are both exponential functions, 4 to the n and e to the n. 4 to the n grows faster than e to the n, so our limit is infinity, so it fails one of the conditions of the alternating series theorem, so this would diverge. And then it failed that nth term test. It wasn't a 0, it was infinity. So the limit as n goes to infinity for that a sub n term was infinity and not 0. All right. Actually, you know what? I'm going to rethink this a little bit. Yeah, because I'm just, sorry. It's a little different order than we normally do things, and there's stuff that I'm used to teaching that we don't have to do anymore. So go back to number 8. So let's revisit number 8. If we're going to use the nth term test, we're not simply applying that idea. So we're going to go back to a previous one as well. We're not simply applying that idea to this like we do with the alternating series theorem, where that just has to be positive and that itself has to go 0. If we're dealing with the nth term test, we have to deal with the entire series and the terms that it would be producing, okay? And what that's going to do is change how we're going to write this here. All right, what our limit is. Still diverges. We're still going to say that it's because of the nth term test. We're still going to say the reason why the limit as n goes to infinity for our series here is now not going to exist. And think about why that would be. If this is a positive number all the time, if we were to graph this, it's going to be like one of the ones we did a couple of sections ago. The overall value of this is going to get bigger and bigger and bigger, but it's going to be bouncing back and forth between positive and negative numbers. So it's going to start close to the x-axis, and then it's going to bounce positive, negative, positive, negative. But if you remember, we graphed some of these that first day. This limit doesn't exist because it's bouncing between positives and negatives because of this element. And then the fact that this gives you a positive number all the time, a bigger and bigger number, our graph would start to look like this. That limit doesn't exist. The same exact thing is going to happen in number 5. So let's go back to this. If we're going to use the nth term test, the nth term test applies to the entire series, not just this. So we are now saying this whole thing here, this limit then for the exact same reason we just talked about would not exist. We don't have to then say that it doesn't equal 0. Clearly if it doesn't exist, it doesn't equal 0. And that's because, again, this guy is going to become an increasingly large number. But since we're going to be bouncing back and forth between positive and negatives, we're close to the x-axis initially. But as that number gets bigger and we bounce back and forth between positive and negative, we're diverging. Okay, we don't have any limit at all. Okay. Hopefully that makes sense. Sorry. You're guinea pigs for the new leaner version of this chapter. Number 9, this one we're back to something nice. This should alternate us as long as this stays positive the whole time. So anywhere between the 1 and the infinity, we should be good. So as we plug those in, the only thing that would then need to happen is this would need to decrease towards 0 as n goes to infinity, and then n cubed grows faster than n to the first. All right, our bigger degree is in our denominator, so this is all good. Converges, and then that's the alternating series theorem. Shorten it up even more. Don't do that in the AP test. Make sure you write it out. All right, 10. Same idea, alternating. If I start throwing in 1, 2, 3, 4, 5, would this ever, make sure we always get positive numbers? And we would. And then we just have to figure out what is our limit as this goes to infinity. So a little mess here. Let's simplify a little bit. You would get n minus 1 squared over 3n squared plus 3n. So what we would notice is we have a degree of n on top, or 2 on top. The degree in our denominator is 2 on the bottom. So these are the same degree. As n goes to infinity then, let's even write this out one more time just so there's no question here. N squared minus 2n plus a 1 if we simplify it. And then this is 3n squared plus 3n. So now as n goes to infinity with these degrees the same, this limit should be 1/3. And it has to be 0. So this one would diverge in term test. And the reason it fails the end-term test is our limit as we go to infinity for the series or sequence, it would not exist. This one even might make more sense in terms of what I was explaining. This should, so think about this as 1 and this as -1. If we're saying that our limit is a 1/3 here, and we're going to be bouncing back and forth between positive and negative, over time it really just becomes positive 1/3, negative 1/3, positive 1/3, negative 1/3, positive 1/3, negative 1/3. That's why our limit would not exist. Okay. 11, I'm going to rewrite this as well as n squared times 2 to the n over a 3 to the n. I am looking at this one. See, I forgot the alternating component to this. So we're going to add that right now. So throw in front of this a -1 to the nth power so that we're still dealing with an alternating series. So if this is alternating, we just need to make sure that this here is positive all the time, which it would be. We throw our 1 through infinity into this, so it's going to be positive, and then does this guy decrease towards 0? Okay, so as n goes to infinity, again, this guy really becomes trivial, the n squared, as we go to infinity. It's, he's playing JV basketball, and then the exponential functions 2n and 3n are playing varsity basketball, so he doesn't really have much impact on anything. He's kind of the freshman that nobody really worries about. The race would really be between these guys. It doesn't matter that n squared and 2 to the n are teaming up. So the 3 to the n as an exponential function, and again, if you have your calculators, you could test that, graph them, and see that. But 3 to the n is going to grow faster. So that does, in fact, tell us that this is true, that this will go to 0. We don't have to worry about possibly not. And so this should converge. Alternating series theorem. Okay, 2 more, I think, yeah. Number 12. Pretty straightforward. This should alternate us as long as this stays positive, and it would. And that just means, does this decrease towards 0? And it does. All right, bigger degree is in our denominator, so converges. Alternating series theorem. Okay. And then 13. This is a big one. We'll deal with a lot of factorials, I believe, in the next lesson. That is something that we need to deal with some more. So this is our factorials. So if we do the alternating part, this is going to alternate. So we're really just worried about this. And as n goes from 1 to infinity, would that always spit out positive numbers? The answer is yes. And then the question is, does this decrease towards 0, which really is asking you the question, which would grow faster? Factorials grow incredibly fast. They're the fastest function that we've talked about yet. Here we're taking our n factorial and squaring it. Here we are taking our 2n, putting parentheses around it, and then we're doing our factorial. So if we were in class today, I would probably be asking you, who wins that race? Would the n factorial, let me put a question mark here because we don't know that yet, would the n factorial and then get squared grow faster than doing a 2n, then doing your factorial? All right, so I should play that little Jeopardy music now. You can think on that a little bit. You could pause, see what you think. Just so you believe me, so you don't think I am lying, we'll look at our calculator here, because the calculator never lies. So I have put this in. So this is the n factorial, can I write? N factorial squared. All right, and then y sub 2 is the 2n with parentheses and then our factorial. So when I go to my table, y sub 1 table is going to be the squared term. Y sub 2 is going to be the product of x with 2, and then our factorial. And then we will see if you are correct. So I will go to my table. Again, y sub 1 is the squared term. Y sub 2 is not. So here is our table. Oh, I'm too far down. I blew it. So let me continue to go up here. Come on, now it's frozen. Went too fast. Anyway, you can see it right now. Okay. It didn't take very long. That you can see, let's say at 7, this is e to the 7th, this one's e to the 10th, e to the 9th, e to the 13th, e to the 11th, 15th, 13, 18, so on and so forth. If we were to continue to scroll on down here, oh, here we go. So pretty much right from the beginning, the one on the right is faster. And as we scroll on down, that difference becomes bigger and bigger and bigger. So what that is telling us is y sub 2 is the faster growing function. So y sub 2, just so you believe me, is that 2x factorial term. So what that then tells us is, since this guy is our winner, he is a faster function than the n factorial, we can get rid of the question mark. As this goes to infinity, this does in fact go to 0. So we can say that this converges. And we can say because of the alternating series theorem. Okay. So hopefully not too bad. I left some problems from the textbook. If you have that, you want to try some on your own, make sure you're squared away with all of this. Totally up to you. But that's pretty much all we got. So let me know if you have any questions. Hope everybody is well, and then I will see you next week. I will probably post that fourth review sometime today. You have until next Tuesday would be the next time I'm really supposed to present anything else to you. So plenty of time to get that done. Any questions, reach out. Hope all of you are well. Have a good weekend.